ladies and gentlemen, welcome back for another round. This is Mr. Doolin, and I thank you for tuning in. What we're going to do today is we're going to take a look at balancing chemical reactions or chemical equations. There's two different areas or avenues that we're going to be looking at here. The first is the law of conservation of matter, and then the second is actually the law of conservation of mass. Now, each one of these has their own particular nuances for how we do it. The biggest one that we'll use most often is balancing based on the law of conservation of matter. And essentially what this is going to tell us is that the number of elements or polyatomic ions on each side of a reaction must be the same, because we can't create or destroy matter. So if I have 55 hydroxides on one side, I've got to have 55 hydroxides on the other. And so what I've got written here, essentially what I just said, is that the number of elements or polyatomics, because we're going to keep polyatomic ions grouped together if we can, must be the same on both sides of a reaction, which is now what we're going to refer to as both the reactants or the product side. All right? And so we'll do a couple of examples of this, but first I want to also introduce the law of conservation of mass. And essentially the law of conservation of mass says a very similar thing, but now rather than dealing with individual elements or polyatomics, we'll actually be dealing with just overall masses that we're going to add into a reaction, or I guess get out of a reaction. And so essentially what we're going to say again is total mass of reactants and products must be the same. And so again, an easy way to write that here is that the total mass of reactants equals, and don't forget the equal sign, I know it's over here in the corner of the page, must equal the total mass of the products. And so we'll look at both examples today. We're going to start with law of conservation of matter. And so we'll look at balancing with the law of conservation of matter. The first example that I'm going to do with you here is just a simple one. It's nitrogen plus hydrogen gives me ammonium. Ammonium is NH3. It's the name of NH3, or nitrogen trihydride. And so remember, nitrogen and hydrogen, those are my diatomics. If I say nitrogen, I mean N2. If I say hydrogen, I mean N3. And then just to make sure we're on the same page, we understand that the left side of my reaction are reactants. The right side are products, all right? And so now what we need to do is we need to figure out, and we start looking and say, okay, well on the reactant side I've got two nitrogens. On the product side I only have one. And then my hydrogens also, they do not balance out. I don't have the same number of elements on each side of my reaction. So now we're going to go through how we're going to do this. I use what's called the inventory method. You can use whatever method you want, but this is an easy way that keeps me accountable for counting the number of elements on each side. So first thing I'm going to do is I'm going to take an inventory. So notice I write the elements, all elements that are present, underneath the reaction arrow. And what I do is that keeps my reactant side counts different from my product side counts. So I see I've got two nitrogens, I see I've got two hydrogens, right? On the product side, I see I've got one nitrogen and I've got three hydrogens. So the inventory method is very purposeful and very deliberate in saying that, okay, now I see that they are not equal. So now it comes down to how do I change the number of elements on each side of a reaction? Well, when balancing, you never change subscripts, because if I change the subscripts, I've actually changed the whole dang reaction, right? My compounds aren't what they would be when they originally had the original subscript. So really big on your paper, I want you to say when balancing, never, and capitalize all of never, change subscripts. So Mr. Doolin, how do we change the number of elements? Well, we can add coefficients anywhere that's necessary to balance these things out. And so what I'm going to do is I'll come up here, and I see that nitrogen has two on the reactant side and only one. So I need more on the product side. So I'll come up here and say, how many more? Well, I need two more. So now 2 times 1, because we always do, what I'm going to write here is coefficient times subscript equals the number of atoms. All right, so coefficient. So coefficient is 2, subscript's 1, 2 times 1 is 2. And notice I've actually crossed out what's originally there and then updated the particular number. And I like this method because it helps me keep track, and if I make a mistake, I know where to back up to. Now, also, by putting a 2 in front of this compound, I've changed the number of hydrogen atoms as well, so 2 times 3 is equal to 6. All right, so now I see my nitrogens are balanced, my hydrogens now are not, and ask the question, which side need more? Well, my reactant side needs more, so I know I'm going to come over here and put a coefficient. I know 3 times 2 would give me the 6 that I want. And now, all of a sudden, I see, based on the inventory method, the number of atoms on each side are equal. My reaction is balanced based on the law of conservation of matter. And my final mole ratio would be 1 to 3 to 2. So notice when I write my final mole ratio, all I do is I just take the coefficients in the order that they appear and just write them out. All right? Okay, let's do another example. All right, and so here I've got my second example. And pause the video, take a second to write it down, but I'm just going to go ahead and go. So I'm going to make my list here. I've got calcium. I've got phosphate. I know PO4 is phosphate. Notice I write the phosphate polyatomic in my list. I don't separate polyatomics as long as they appear on the reactant side and on the product side, and this is the case for phosphate in this particular reaction. Then I've got sodium and I've got chlorine. So now I'm just going to update my counts and take my inventory. I've got 3 calciums, 2 phosphates, 1 sodium, 1 chlorine. On the product side, now it gets a little bit tricky because I write these in order as to how they appear on the reactant side. They're not in the same order on the product side, so I need to be a little bit more careful about where I'm putting my counts at. Calcium's over here, there's only 1 of them. Phosphate's right here, there's only 1 of them. Sodium, I have 3, and then chlorine over here, I have 2. And again, I'm looking, I don't have everything balanced, and it's really easy to see again with this inventory method, so I just get to it. I always start normally at the top of my list here. I've got calcium. I need 3 over here, so go ahead and update this. That gives me 3, and then it gives me 6 chlorines, all right? And then let me change colors here. Then I'll go, the next one is phosphate. So I need 2 phosphates, so again, I'm going to put a coefficient rather than putting any subscripts, and that gives me 2 phosphates, not 8, because remember, this is part of phosphate, so I'm treating it really in this particular case as that, right? I don't multiply that subscript by of the phosphate itself, because that's contained here in my list. And then also that gives me 6 sodiums. So now calcium's balanced, phosphate's balanced, and then sodium coming over here, I'll put a 6 there, and that gives me 6 sodiums and 6 chlorines. I see by the inventory method, now I am balanced, and I've got a 1 to 6 to 2 to 3 ratio. All right? Okay, and then something else that I'm going to tell you here, ladies and gentlemen, is that sometimes when I'm balancing these things out, I'll have to unbalance something I've already previously done in order to balance a new one, and that's okay. Just by the end of this, by the end of the whole process, everything should be balanced, all right? Okay. And then the last example I'm going to do with you is actually a hydrocarbon. Hydrocarbon combustions get a little bit funky sometimes in that I end up with odd numbers with my elements. All right, and so there we go. I've got a hydrocarbon combustion listed out here. Again, same thing, just going to make my list. I've got carbon, hydrogen, and oxygen. And just FYI, hydrocarbon combustions will always just be CHO. All right, so do my counts. I've got 2, 6, and 2. I've got 1 carbon. I've got 2 hydrogens. And now here I've got 3 oxygens. Because notice, this is total, right? I've got 2 oxygens here plus 1 oxygen in the water. So I have to make sure that I'm keeping that count correct in my list and always adding both of those together to get the total for that particular side of the reaction. So now I get to balancing. All right, I'm going to go balance carbon, so I'll put 2 there. Well, that changes that, and now notice I've got 2 times 2 oxygens, but I have to add this over here. So I've got 4 here, and then that would give me 5 oxygens, right? Okay, and then now what I'm going to do is I'm going to go to my hydrogen. I've got 6 over here. Over here I've got 3, so I'm going to do 3 right there, and that would give me, 6 hydrogens, and there's 3 plus the 4 would give me 7 oxygens. Now, here's a very common problem that I run into when I'm balancing hydrocarbon combustions. I end up with this odd number of oxygens, and I can never make this even over here equal to the odd. All right? Not with the whole number coefficient anyways. And we're going to deal with whole number coefficients starting here. When we get up to AP chemistry, we'll understand that fractional coefficients are acceptable, but for right now, we're going to leave everything as a whole number coefficient. Okay? And so how do we change an odd number to an even number? Well, the easiest way is to multiply everything times 2. So what I'm going to do is I'll come up here and I'll just double all the coefficients that I currently have Notice this is understood to be 1, so that would become 2. And then I'm going to update all my counts. So everything would just double. So that would become 4, that would become 12, this would become 14, this would become 4, and this would become 12. Notice I didn't change the oxygen because I didn't change any of the coefficients on the oxygen there. I'm going to leave those by themselves, all right? Okay, so now I can actually balance the oxygens because if I come over here and just put a 7, that gives me 14 oxygens. Now, a couple of you are looking at this and you're like, oh, wait, well, what happened? Well, the number of odd oxygens that I had actually always becomes the coefficient on the oxygen there. And if you're going to use that trick and that shortcut, just make sure you remember to double all of the other coefficients, okay? So we end up with 2, 7, 4, and 6. And then the other thing that I'm going to tell you right now, and I want you to write it down and remember it as a rule, is that if we ever end up with an element in 2 different places on the same side of a reaction, we always want to balance that last. Don't try and start with that because it gets too complicated and you have to end up guessing too many times, all right? So always balance elements that appear in more than one place. Balance them last, all right? Okay, so now what we're going to do is we're going to move on and we're going to take a look at balancing with the law of conservation of mass. And I'm just going to abbreviate this, right? Law of conservation of mass. And so what does this actually say? Well, I'm going to give you an example here. 2KClO3 gives me, it decomposes to 2 KCl plus 3 oxygen. So potassium chlorate breaks down and decomposes to give me 2 potassium chlorides plus 3 oxygens. Now, how does the law of conservation of mass work? Well, generally when we're doing this, we're dealing with masses. And so in a lab, if I took potassium chlorate and I heated it, this is a thermal decomposition, and I'm going to say, hey, I decomposed this. I got 30 grams of potassium chloride left. How much oxygen did I actually produce? Well, I know law of conservation says reactants and products should be the same. And so this, if I have 50 total grams of reactants, I should have 50 total grams of products produced. And so you notice with this, what I can do is just use some very simple math to say, well, this should be actually 20 grams because I should have 50 total grams of product, all right? Now, we can do this stoichiometrically, but the easy way, since I'm only missing one mass in this, and I know the law of conservation says both sides of my reaction should be the same, then I can actually very easily and very quickly just use addition and subtraction on this to figure out what that missing number is. Now, could I convert 50 grams to grams of oxygen and do a grams A to grams B stoichiometric conversion? The answer is absolutely 100%, but this is just a kind of a shortcut method when we're dealing with masses, and it only works when I have the masses of everything else involved in the reaction and I'm only missing one, okay? All right, ladies and gentlemen, that's all for today. If you have any questions, make sure you get them down in your notes. Come to tutorials, we'll get those taken care of, and otherwise I will see you in class.